Welcome, and thank you all very much for coming along, and a particularly warm welcome to anybody who has never been to a Gresham College lecture before. I hope this will be a start of a new tradition for you, and I think we have some sixth formers here, so hi. Well, let me tell you what I want to do in this talk. I want to do several things, and the first is to introduce you to the remarkable mathematician Leonhard Euler, and then introduce one of the most important natural numbers, the number e. And I'm going to give some examples of where it arises naturally in exponential growth and exponential decay. But the finale of the lecture is to show you a remarkable connection between the exponential and the trigonometric functions and some of this connection's beautiful consequences. So let me start by introducing Euler. His life can be conveniently divided into 4 periods spent in only 3 locations: Basel, St. Petersburg, Berlin, and then back to St. Petersburg. He was born in Basel in Switzerland in 1707 and spent his early years in a village nearby where his father was a Calvinist pastor. He entered the University of Basel when he was 14 and received instruction there from the great Johann Bernoulli, who was then probably one of the world's greatest mathematicians. And Euler graduated in 1723. He started to develop an international reputation when he was only 19, when he submitted an entry to the Royal Academy of Sciences in Paris for a competition on the best way to position the masts on a sailing ship. Euler didn't win the highest prize, but he did receive an honourable mention. In the future, he would win the highest prize on no less than 12 occasions. 1727 was the year that entry was published, and also the year that he moved to a professorship in St. Petersburg. It was also the year that Isaac Newton died. The St. Petersburg Academy had been founded by Peter the Great and was part of his plan to reform the Russian educational system and open Russia to the world. Euler stayed in St. Petersburg until 1741, when, because of the political turmoil in Russia, he accepted an offer to move to the Berlin Academy, where he was initially very satisfied until friction developed between him and Frederick the Great, which resulted in Euler, in 1766, returning to the St. Petersburg Academy. Russia was now ruled by Catherine the Great, who was again, like Peter the Great, making education a priority for the Russian government. Euler stayed in St. Petersburg until he died in 1783. Here I've gathered together several portraits of Euler. On the left, we have a painting from when Euler was about 30. In the middle, there are 2 portraits of him for when he was in his 40s. And on the right, a portrait of him in his early 70s, about 5 years before his death. During his first spell in St. Petersburg, he married, producing 13 children, only 5 of whom survived past childhood. And of those 5, just 3 outlived their parents. Euler had health problems of his own, and you can see that in some of these portraits. By his early 30s, he had lost the vision in his right eye. As we will see, it did not affect his productivity, and even the loss of sight in his other eye in 1771, leaving him essentially blind, did not seem to slow down his prodigious mathematical output. In fact, during this time of essentially total blindness, he produced some of his most important work. Euler had an amazing memory, was able to hold many abstract ideas in his head simultaneously, and was also able to undertake staggering calculations in his head. The mathematician Francois Arago wrote, "Euler calculated without apparent effort, as men breathe or as eagles sustain themselves in the wind." And Euler kept working at mathematics until the day he died, as was described by the Marquis de Condorcet in his eulogy for Euler. He wrote, "He had retained all his facility of thought and apparently all his mental vigour. No decay seemed to threaten the sciences with the sudden loss of their great ornament. On the 7th of September 1783, after amusing himself with calculating on his slate the laws of the ascending motion of air balloons, the recent discovery of which was then making a noise all over Europe, he dined with Mr. Lexell and his family, talked of Herschel's planet, and of the calculations which determine its orbit. A little after, he called his grandchild and fell a-playing with him as he drank tea, when suddenly the pipe, which he held in his hand, dropped from it, and he ceased to calculate and to breathe. But why did Condorcet call Euler science's great ornament? To give some indication of why, let me consider Euler's work under three dimensions of quantity, range, and significance. First of all, quantity. He produced over 800 books and papers in a wide range of areas that I'll come to shortly. Indeed, 228 of Euler's papers were published after he died, making the deceased Euler still one of the world's most prolific mathematicians. The publication of his collected works by the Euler Commission in Switzerland began in 1911, and to date 76 volumes have been published. 3 volumes of his correspondence have also been published, and several more are in preparation, so the exercise isn't over yet, over a century after it began. At the bottom of the slide, I've put a screenshot of the very useful Euler Archive website, maintained by a group of scholars and hosted by the Mathematical Association of America. And in the Euler Archive, you can access a list of 866 of Euler's books and papers. You can also choose to see the titles in English, and you can click through and actually get through to the original documents or the documents in translation for many of them. Now, here what I did, just to give an idea, was to take a random, and it was almost random, a screenshot of 19 of them. That's just over 2% of them, to give some indication of the range. And here we are. I'll read them out because it's a little bit small, but the first 3 are concerned with the motion of fluids. General principles concerning the state of the equilibrium of fluids. General principles concerning the motion of fluids. And then research on the theory of the motion of fluids. Then he switches to excuse me. You see how excited I am by this. Then he switches to number theory on the numbers, which are the sum of 2 squares. Back to mechanics on the construction of gears. The elements of the doctrine of solids. Proof of some of the properties of solid bodies enclosed by planes. And I was delighted when as I say, my random snapshot, because this is the topic I spoke about last year when talking about surface topology, about Euler's formula for a polyhedron, connecting the number of edges, faces, and vertices. So it was lovely to see it come up, as it were, randomly here. Celestial mechanics on the movement of celestial bodies perturbed by any number of forces. Refined study into the effects of windmills. Experiments to determine the refraction of all types of transparent liquors, so into optics. On the action of saws. Explanation of certain paradoxes in the integral calculus. Now on to magnetization. Research concerning the declination of the magnetized needle. Back to architecture or structures concerning the strength of columns. Back to optics, telescopes and microscopes. Optics again, research into glasses. And then my second delight at having chosen this page, proof of a theorem of Fermat that every prime number of the form 4n plus 1 is the sum of 2 squares. Just over 2%. So you can see his range was from pure topics such as number theory, combinatorics and the geometry of a circle, via mechanics, logarithms, infinite series and calculus, to such practical concerns as optics, astronomy and the stability of ships. But quality and range are not the most important dimensions of Euler's activity. Of greater importance was the significance of his work. So many crucial and core ideas in mathematics can be traced back to his work. I've just taken some of them. He introduced the symbol E for the exponential number, which will form a major part of this talk. F for a function and I for the square root of -1. And let me just briefly look at some of the contributions he made to mathematics. While at St. Petersburg, he became interested in infinite series. It's the case that the harmonic series of reciprocals, 1 plus a half plus a third plus a quarter and so on, has no finite sum. It keeps increasing. But Euler noticed that adding the first n terms of this series up to 1 over n gives a value very close to log n. And in fact, He demonstrated the difference between them, that's the sum of the first n terms of the reciprocals, minus log n, converges to a limiting value very close to 0.577, now called Euler's constant. Just mention another one because it's the one that helped make his international reputation. And it involved the infinite series known as the Basel problem, which was the sum of the squares of the reciprocals of the natural numbers. So that's 1 plus a quarter plus a ninth plus a 16th plus a 25. And of course, people had calculated, knew what the answer was approximately, but no one could find its exact value. And Euler achieved fame by showing that the sum is pi squared over 6. So the sum of the squares of the natural numbers is pi squared over 6. And I'll make a comment about the nature of his proof at the end of the lecture, because it's part of a pattern of how he did mathematics. And he then went on to find the sum of various other powers, even powers up to 26. And on the right, I've got the title page of Euler's Introduction to the Analysis of Infinite Quantities of 1748. That discussed infinite series, partitions of numbers, the exponential function, the properties of conics, and many other. And this book is the first that many people think, sometimes said, that looks modern to our eyes. It makes the concept of function crucial, central to mathematical analysis, rather than that of curves, rather than the geometrical approach. And in it, Euler introduces the special functions, the polynomial, the trigonometrical, the exponential, the logarithmic, the inverse trigonometrical, and they are still center stage in mathematical analysis. He also found some of the most beautiful formulae in mathematics. And although the style of modern mathematics is very different today, we're now more concerned with concepts and structures. Its most important results still frequently involve formulae. Euler was also a gifted expositor and author. His books are very readable. And one of the most popular of his works, I think it might be still in print today, it's certainly available on the web in various versions, was his letters to a German princess, a survey of popular science and philosophy written for the layperson, as you can see from the description on the title page here. This is a subsequent English translation, and I'm showing volume 2 there because that was of the 2 volumes, this was the nicest plate I could find in it, where what Euler is doing is talking about electricity, electrostatics. So here he has, I think that may say positive electricity, and here he has negative electricity, and which you obtain by rubbing different things against different other things. All right, let's come to the main body of what I want to talk about, and that's to link the exponential function with the trigonometric function. And you've probably heard of exponential growth, means something that grows very fast, and I'll be looking at exponential growth and also looking at exponential decay. And frequently you'll see expressions such as 2 to the n or 3 to the n, and they can become very large very quickly as n increases. But rather than using the number 2 or 3, mathematicians frequently use the number e, which an approximation for which is given up here at the top to however many decimal places that is. And I just want to motivate that number e in what I think is a quite natural, quite accessible sort of way. And we want to do it through financial modelling, where we're going to invest £1 and we have an interest rate which is 100% for a year. Later on I'm going to talk about imaginary numbers, but an interest rate of 100% is more imaginary than any other number you could possibly think of. It makes the square root of -1 seem positively concrete. Well, if you invest your £1 for a year at an interest rate of 100%, you're going to get at the end the princely sum of £2. Okay? But suppose you do the following. You half the interest rate, but you pay it every 6 months. So what you do at the half year is at the end of 6 months, you pay interest of 50%, which means that you're going to have £1.50 at the end of the 6 months. And then at the end of the next 6 months, you pay another 50%, and 50% of £1.50 is 75 pence. So you end up at the end of the year with more money, £2.25. So you get 25 pence more by compounding the interest every 6 months rather than just once a year. So then if you do it every quarter, so you divide the interest rate here by 4, so it's 25%, but you pay it every 3 months rather than paying it every year. And if you go through the same calculation, I've gone through the same calculation, you will come up with £2.44. So you're getting more again. And you begin to think whether or not it will continue to increase or what the long-term behaviour will be. And you can similarly do the same thing, dividing the interest rate by 12, so 100 over 12%, but compounding it at the end of every month, and it goes up to 2.61. And you can see from the table I've done here every day, which I think presumably is what the banks do, but you can continue to go on to do it every hour, every minute, and every second, and when you come down here, you see that it's settled down at least to 4 decimal places. And this number that you arrive at down at the bottom, this number up here, is known as E, and as you can see, what happens when you continuously compound an interest rate of 100% over a period of time. So it arises naturally in a way to do with growth and change. Right? And of course, when you've done that for one interest rate, you can't stop yourself for doing it for other interest rates. And here's a graph where what I've done is to graph along the bottom the percentage interest rates going from 0 here, which just leaves you with your pound that you started off with, up to 190% interest. And I've done a marking on the graph here. Here's the one I did the calculation for. Here's the 100 going up here. And on the vertical axis, we have got the accumulated sum, the result on £1 continually compounded, and that is the number E, 2.71828, to whatever number of decimal places that is. Okay, so let's try and make it a little bit more and pretend we are Euler here, and what we're not going to do is we're not going to think about it graphically, but we're going to think of it in terms of a series expansion. So if we sorry, I just want to say another important reason for having the number E involved is that this is a curve of e to the x, but I've also now included some negative numbers as well as some positive numbers. And I just wanted to make the point that the other thing about the exponential function e to the x, where e is that number that I described, is that it's got the very nice property that if you take any particular point on the curve, the rate of growth, which is given by the slope of the tangent here, is equal to the amount that you have at that stage. So the slope of the tangent at any point is just given by the height of the point that you're at, which is a very unique characterizing feature of it. Okay, so, all right. So let's get a series expression for it. And what you can do after a little bit of work or a little bit of thought is that this process of taking an interest rate of 100%, if you take the number of time periods and call them n, so what you do is instead of paying 100%, you pay 100% over n during each time period. All right, so we've reduced the interest, but we're paying it more frequently, and we're also paying interest on top on interest. Then if you have a chance to sit down and look at it for a while, you're able to see that the accumulated sum at the end of a year is that, 1 plus 1 over n to the power of n. And one can multiply that out. There are n terms multiplied together, or there's a theorem called the binomial theorem, because this expression 1 plus 1 over n is binomial. There are 2 terms in it. And you can multiply it out, and you can ask yourself, what happens as n increases? And you can do the arguments associated with it, and you find out that what you get is this long infinite series here, 1 plus 1 over 1 plus 1 over 2 times 1 plus 1 over 3 times 2 times 1 plus that, which is very much simplified if we introduce this factorial notation. So factorial 5 just means 5 multiplied by all the whole positive whole numbers smaller than it. So factorial 5 is 5 by 4 by 3 by 2 by 1, but it makes the writing of it a lot easier. So we have got here that E is expressed as an infinite series as the sum of this very nice expression 1 plus 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial. And one gets to it as being the limiting behavior of this expression up here, 1 plus 1 over n to the n, which is where you're continuously compounding the interest. And we can do the same for an interest rate of x, or x over 100, rather than an interest rate of 100% that I did there. And the difference that makes e to the x now as an infinite series, and that's going to play a major part in the story I'm going to be telling at the end. Here we've got e to the 1, and I've put the ones that are going to change into x here in blue. But really, because what we're doing is we're now expanding 1 plus x over n to the n. Before we were expanding 1 over 1, 1 plus 1 over n to the n. Now we're expanding 1 plus x over n. And if you do exactly the same thing, exactly the same arguments, letting n become large, you get the series expansion for e to the x. Again, it's this nice one here, 1 plus x over 1 factorial plus x squared over 2 factorial, x cubed over 3 factorial. It's got beautiful symmetry to it. X to the 4th over factorial, 4 factorial, x to the 5th over 5 factorial, and keeps on going like that. All right, so that exponential series is going to be crucial to us because it's going to be the linchpin that underlies the connection between the exponential function and the trigonometric functions of sine and cosine. But we'll leave it for a little time, and we'll go on and look at exponential decay. And I want to illustrate this with a practical example of Newton's law of cooling. And Newton's law of cooling, because last time my lecture was on Newton's laws, and I didn't have a chance to put in his law of cooling, so I make that good now, says that the rate of loss of heat from a body is proportional to the excess temperature of the body over the temperature of its surroundings. And here I've applied Newton's law of cooling to a cup of coffee, which is initially at 80 degrees centigrade in a room whose temperature is 20 degrees centigrade. So the excess temperature, which is what I'm plotting vertically, the excess temperature of the coffee over the ambient temperature in the room is 60 degrees. So that's the temperature of the coffee when it's first made in the room. It's at a temperature of 80, and the temperature of the room is 20, so the excess temperature is 60 degrees. And Newton's law of cooling says that it starts to cool, and the hotter it is, the faster it cools. That's essentially what Newton's law of cooling is saying. As time passes, the coffee gets cooler, and it follows this exponentially decaying curve, and you see it's getting closer and closer. The excess temperature is dropping and dropping. It's getting closer and closer to what the room temperature is. And these exponential curves get a very interesting property, and that's the time for the excess temperature to halve from any value is always the same. So if you ask how long does it take the excess temperature starting at 60 to reduce to 30, to half, we can do that from the graph I've drawn. The expressions are up there. 60 dropping down to 30. How long does that take? That takes 25 minutes. That's why I've chosen the numbers the way I have there, so that I end up with a nice whole number, 25. Right? But the assertion was that no matter what temperature you are, it's going to take the same time for that temperature to halve. So let's see what happens when it drops from 30 degrees down to 15 degrees. And when we do that, we see it's dropping from 30 down to 15, and that happens at time 50 on the clock, which is another 25 minutes. So it takes 25 minutes to halve, and just do it again because when you're on a roll, going from 15 down to 7.5 and 7.5 degrees will occur after time 75, which is another 25 minutes. So no matter what temperature you're at, it takes the same amount of time for that temperature to reduce by a half, by 50%. And of course, that's the similar kind of thing that you get in radioactive decay, where on average, a radioactive element decaying, the half-life is the length of time it takes for, on average, half the particles to have decayed. All right. But now we come to crucially important part of the lecture, which is that the following problem. You just made a cup of coffee. You want to drink it white. Sadly, the phone goes, and you're not able to drink the coffee for several minutes. But you want your coffee to be as hot as possible when you eventually are able to drink it. Should you add the milk before lifting the phone or when you return after the phone call? Now, for those who have never been to a Gresham lecture before, this is the kind of level we operate at. It's important stuff. And believe me, you'll think of it. I thought of it when I was having breakfast this morning. Should I add the milk now or should I leave it? Two arguments you can use here that compete. Newton's law of cooling says the hotter the coffee is, the greater its heat loss. So add the milk right away to reduce the heat loss during the cooling. But on the other hand, adding the milk cools it down. And the hotter it is, because of the mixing effect, the hotter the coffee is when you add the milk, the greater the effect it's going to have. So leave adding the milk for as long as you can. So you've got two competing tendencies, and you need to do the modelling, you need to do the analysis in order to try to decide whether it's better. And I chose 30 minutes, as you'll see in a minute. Add the milk at the start, or add the coffee, or add the milk after the 30 minutes. And we need to use our exponentials to decide between the two of them. It turns out that it's crucially dependent upon the temperature of the milk, because if the milk is at room temperature, and here I've done it, the milk is at room temperature, and we're going to add the milk. So I've got two graphs here according to my two scenarios. This line here is adding the milk at 60. When I add the milk at 60, the temperature immediately drops down, and you can see it drops down to somewhere over 50. Then Newton's law of cooling kicks in, and it subsequently cools and goes down like that. So that's the scenario of adding the milk at the very start. If you decide, on the other hand, to wait for 30 minutes before adding the milk, well, here's the coffee. It starts to cool according to Newton's law. After 30 minutes, its temperature is down here. You add the milk, and in fact drops down to what the previous curve was. So under the assumptions that I'm making, if the milk is already at room temperature, it doesn't matter when you add it. But it's different if you've got your milk in the fridge. Right. If the milk is from the fridge, all right, so what happens there is that it drops down here where we're adding it right away, and then Newton's law of cooling kicks in and it keeps on going. But if you add the milk at the end, here we have it dropping down because we haven't added the milk. Now we're adding the milk and it drops down and it goes lower than scenario 1. So in other words, the best thing to do if you're milking in the fridge is to add it right away. But if your milk is warm, the red milk, warm milk at 35 degrees, it turns out it's best to delay adding it. So once again, we've got the two, adding it at the start, comes right down here, right, and that one stays below, whereas here's leaving it low and adding it later on, coming down, and then drops down, and then keeps on going. So perhaps fairly intuitive that, you know, if the milk's cold, add it right away, and if it's warm, then delay adding it. But in doing this here, I've made lots of simplifying assumptions to do it, and it turns out, in fact, that a lot of them don't actually matter too much, such as the volume heat capacity of milk and black coffee are the same and close to that of water. It doesn't turn out to be too crucial. But there's one that does make such a big difference, which is that black coffee and white coffee cool at different rates. And this was the subject of this paper on cooling tea and coffee by Rees and Viney. They were at that time Cambridge physicists, are based in Cambridge, and I suppose you have to do something in Cambridge in the winter. But what they found was that in the abstract, factors influencing the rate of cooling of hot coffee and tea have been investigated theoretically and studied experimentally using deliberately domestic apparatus. It is demonstrated that black coffee cools faster than white coffee under the same conditions. Under most, but not all circumstances, if coffee is to be as hot as possible several minutes after its preparation, any milk or cream should be added immediately rather than just before drinking. Add your milk or cream immediately. And they conjecture that the mechanism causing the difference in cooling rates is a reduction in evaporation rate when the milk is present in the coffee. And I'm sure you've heard of the beverage called Irish coffee, which is a mixture of coffee and whiskey and cream. And I'm going to experiment over Christmas to see whether having the cream in the top, which will reduce the evaporation rate, has a different cooling rate to the mixing the cream in, and I'm also going to explore the effect of having different amounts of whiskey in the coffee. And I shall report back at my Fourier lecture, if I can remember. So now to the crux. Possibly Euler's most celebrated achievement was to link the exponential and trigonometric functions together. And a consequence of that relationship is this, which many people consider one of the most important, most beautiful relationships in mathematics, relating the 5 most important constants in mathematics. We've got 0, the identity for addition, 0, which when added to any number leaves the number unchanged. We've got 1, which is the number which is the identity for multiplication. 1, which multiplied by any number leaves the number unchanged. E, I've been telling you about, the exponential function defined above. Pi is the ratio of the circumference of a circle to its diameter. And I, which is the square root of -1. And I want to say a little bit about the square root of -1 and hopefully remove the magic from it, because although Euler worked with the square root of -1 a lot, he said, of such numbers we may truly assert that they are neither nothing, nor greater than nothing, nor less than nothing, which necessarily constitutes them imaginary or impossible. And I want to try and prove to you that he was wrong. He was wrong here. So this, I think, is interesting. And when I first met this, whenever it was, I thought it's quite nice. Because even in the 19th century, there's still a great deal of unhappiness about complex or so-called imaginary numbers. And it was William Rowan Hamilton, an Irish mathematician, who finally provided an explanation for complex numbers that was generally accepted. All right. And what he proposed was that a complex number is no more than a pair of real numbers. Now that's, as long as you are content with real numbers, you feel that you know them like old friends, I'm saying to you a complex number is just a pair of them. All right. But I have to tell you some more. I have to tell you how to add them, and I have to tell you how to multiply them. But what I'm doing is telling you how to add and multiply pairs of real numbers, and pairs of real numbers you said you were happy with. Well, some of you are nodding. I think it is an agreement. And some of you got your eyes closed because you're concentrating that much. They're added as follows, very straightforwardly. You've got the pair of real numbers 1, 2, and the pair of real numbers 3, 4. You add them just by adding the first member of the first pair to the first member of the second pair, and the second member of the first pair to the second member of the second pair. And that's an example there. Addition straightforward. Multiplication messier. They're multiplied as follows. It's a strange way of multiplication, but it's just a way of combining. Multiplication in the sense of combining 2 of them to get another one of them. Right? And so what we do here, we have AB times CD, and it is going to be the first by the first minus the second by the second, AC minus BD, and then it's the outside one, AD, A by D, and plus BC. So whatever its benefits or whatever you may say, why do it? But there's no disagreement. You can't disagree that it's just operating with these concrete things, pairs of real numbers. And here I've done it with an example. All right, here 1, 2 times 3, 4, and hopefully it's correct. All right. But now we make an association, just a correspondence. All right. What I'm going to do is to think of the pair A0, and the important thing is that there's a 0 in the second entry. And I'm going to think of that as corresponding to the real number A. And I'm going to think of the pair 0, 1. 0, 1, just an ordinary pair of real numbers, corresponds to the imaginary number I. Now, if it does correspond to the imaginary number I, what property should it have? It should have the property that when multiplied by itself, it gives you -1. That's what I does. So let's take this pair, 0, 1, multiply it by itself according to this rule, and see if it comes up with the answer -1 times 0, because that's corresponding to it. And it does. Because if you take this pair 0, 1, 0, 1, apply this rule to it for multiplication, what you get is that the first entry here is -1 and the second entry here is 0. So with the correspondence, we can write that as I times I is -1. So all I want to convince you about is that you don't have to use the symbol I. You can recast all of complex analysis if you want in terms of these pair of real numbers using this notion of multiplication and this notion of addition. And so that's dispelled that magic until I show you something at the very end which will bring the magic back again, and the mystery certainly. Okay, and here's another way of thinking of it geometrically, representing complex numbers in the plane, which is quite a useful way of thinking about it. But next, let me introduce the next main players, which are the trigonometric functions. So what we have here is we have a unit circle, a circle of radius 1, and we've got a point that is moving uniformly around this circle at a certain speed, right? Constant angular speed. And then what are the sine and the cosine? Well, the sine is just going to be the height of the point moving around the circle above the horizontal axis, and that's just given by this curve here. All right. What is the cosine? Well, the cosine is going to be the distance that the point is away from the vertical axis, and that's this one here, giving you the cosine. All right. So geometrical, and for what's going to come, it'll be convenient to measure the angle in radians, and if you've got a circle of radius 1, the radian measure of an angle is just the length of the arc that it subtends. So if you have an angle like so, it's just the length of the arc if your circle is a radius 1. So it's a geometric definition of the trigonometric and of the cosine and cosine functions as being the distance of this point as it rotates around the circle away from either the horizontal axis or from the vertical axis. Right. But that's not the way Euler works. Euler works with infinite series. So let's see him create an expression, find an infinite series for both the sine and the cosine. All right. Just want you to get the feeling for this, to see the kind of thing that he does. First of all, it's really not hard if you had a chance to look at it. To find it's using what's now called, for our sixth formers here, de Moivre's theorem, and also uses the binomial theorem, to find an expression for the cosine of a multiple of an angle. Theta is the angle, and n times theta is a multiple of it. So this is finding an expression for the cosine of an angle, all right, in terms of powers of cosine of the angle and powers of the sine of the angle. So it's relating the cosine of a multiple of an angle to powers of cosine of the angle and sine of the angle. And there's a few lines that go before that using this result called now called de Moivre's theorem, and using the binomial theorem. That's a binomial expansion on the right-hand side, terms just multiplied together. Now watch Euler at work, consummate mastery. He says, now let theta be infinitely small, and let n be infinitely great, but that's not all, in such a way that their product remains finite and equal to some number x. So let one of them get smaller and smaller, the other one get larger and larger, but all of the time, the product of the two of them always gives you x. When you do that, it turns out he replaces, the cosine theta can be replaced by 1, because theta is getting smaller and smaller and smaller and smaller, and for the same reason, the sine theta can be replaced by theta. So you're going to get theta times n, another theta times n, which is the thing that we are calling x. So from that expression there, by letting something get very small, getting something get very big in such a way that their product remains the same, he gets a series expansion for the cosine of x. And here it is here. Cos x is equal to 1 minus x squared over factorial 2, the factorial function again, x to the 4 over factorial 4 minus x to the 6 over factorial 6. So the cosine only involves even powers of x. and alternating signs going along here. So the graph of it's going to be an even function. Do exactly the same thing as I said on the previous slide for the sine of x. Write out the sine of a multiple of an angle in terms of powers of the sine and cosine of the angle. Then you get that sine is going to be a power series involving odd terms, x to the 1, to the 3, to the 5, to the 7, to the 9, to the 11. So it only contains odd powers of x, and it contains 3 factorial, 5 factorial, 7 factorial, and 9 factorial. And for it to have this form, we want to take x measured in radians. Right. Now, maybe if you're thinking back, you're already beginning to see what Euler does next, because here we've got this series expansion for cosine, series expansion for sine, and the other series expansion we had was for e to the x, remember? And that contained all powers of x's, and it had factorials on the bottom. Okay. The only thing that's a bit awkward is the pluses and the minuses. No, the pluses aren't awkward. The minuses are awkward. Because we didn't, if I go right back, if you don't want you getting dizzy now. Does it seem more understandable if I go backwards? There you are, down at the bottom. All the powers of x with the appropriate factorial underneath it. And what we have got is the sine and the cosine as power series where the same kind of things occur. There we are. But with minuses into it. But minuses are okay because we now have the number I. And remember what I does. I multiplied by I gives you minus 1. Well, let's see if we can bring that into it. The result we want to show that Euler discovered and proved this way, e to the ix is the cosine of x plus I times the sine of x. And you just have to keep confidence in yourself. Cosine of x written out there. You've seen that, so you don't have to think beyond that. You now believe that. Sine of x is written out here, and I'm multiplying it by I sine of x, ix minus I times x cubed over factorial puts ix to the 5 minus so on. All I've done is put the I in. Now I'm going to add them together. I'm going to add them together, and I'm going to rearrange so that I do it increasing powers of x. 1 plus I times x minus x squared over factorial 2 minus I times x cubed over factorial 3. So I'm just interleaving the two series so that they have they're in ascending powers of x. So now you see that along here, and I'm saying that is exactly the same as e to the ix. E to the ix, 1 plus ix, there we are, plus ix squared over factorial 2. Now, ix squared is going to be I squared times x squared, and we know that I squared is minus 1. So that's giving us the minus x squared over 2. And the next one is ix cubed. Well, here, I'll put it in a slide up here. We're using the fact that I squared is minus 1. I cubed is going to be minus I, because I cubed is I squared, which is minus 1 times I. So it's minus I to the 4th brings us back to 1. I to the 5th will start it over again. So it repeats in blocks of 4 as you go up, running between 1, minus I, and 1. So when you add those two things, you get this, which is just e to the ix down here. So you can nearly see, perhaps, once it's expressed in this way, this partitioning of this breaking up of the series for e to the ix into two sub-series, one of which is the cosine and one of which is the I times the sine. Now, once you have that, you can start to get some lovely results coming out of it. So let me give you... here's the Euler's formula in Introductio, which I didn't get from the Euler website, the Euler archive. The Euler archive has got I think this is the first edition, has got a subsequent edition with commentary on it. But unfortunately, it breaks this formula over a page, the most important formula in it, and it's broken up over a page. So this is not quite as good resolution of it. But the formula is down here, e to the... Yeah, he wasn't using the symbol I here at the moment. there we are. If I'm just patient, I've lost, that seems to have stopped working. Third line up, you see the Euler formula. E to the plus v square root of minus 1 is the cosine of v plus the square root of minus 1 times the sine of v. And the sentence above that says it says it in Latin, from which it can be worked out in what way the exponentials of imaginary quantities can be reduced to the sines and cosines of real arcs, of real distances. Right? Now, to find this lovely relationship between the 5 constants, e, I, pi, 1 and 0, all we have to do in this formula here is to set x equal to pi. If you set x equal to pi, you get e to the I pi is cosine pi plus I sine pi. Now I use the fact that you know what the cosine of pi is. The cosine of 180 degrees is minus 1, and the sine of pi is 0. Substitute those numerical values in, and you get e to the I pi is minus 1, or rearranging it, which is the way I like to do it, e to the I pi plus 1 equals 0. Really rather very nice indeed. But there's another one, which is that you put x equal to pi there. What happens if you put x equal to some other value? Let's say pi over 2. So if you set x equal to pi over 2, and use the cosine of pi over 2 is equal to 0, then the cosine of 90 degrees is 0 and the sine of 90 degrees is 1. You'll get a certain expression up above. Then raise both sides to the power of I. And what you end up with is that I to the I, this is the complex number, the square root of minus 1, to the power of the square root of minus 1, comes out to be 1 over the square root of pi. So I to the power of I, the thing about it is it's a real number. It happens to have that value, 1 over the square root of e to the pi, but more surprisingly is it's real. And the mathematician Benjamin Peirce said about this formula, we have not the slightest idea of what this equation means, but we may be certain that it means something very important. All right. Well, let me try to pick out, just coming to the end now, some of Euler's characteristics. There was his manipulation of symbolic expressions. He had a fantastic ability to manipulate symbolic expressions. And we saw examples of his symbol manipulation in his work on the infinite series view of the exponential and trigonometric functions. And Euler has the reputation of being probably the greatest symbol manipulator ever. And we also saw how he treated the infinite. He used infinitesimals, infinitely small quantities, and infinitely large quantities, with a dexterity and a sure-footedness that is awe-inspiring. We saw in his work on the series expansion for cosine how he would let one quantity become infinitely small and the other infinitely large, but in such a way that their product remains constant. Mathematicians know that dealing with infinite processes and limits can give problems, but Euler seemed to have an unbelievable intuition that carried him through. The other thing I want to pick out is strategy. We've only seen one or two examples of it, but a favourite strategy of Euler was to view the same thing in two different ways. We saw how he showed a particular infinite series was the series for the complex exponential, but could also be split into two other series, which were the series for sine and cosine. And this ability to view mathematical objects from different perspectives is one of Euler's core strengths. But of course, having said all of that, even having identified the three characteristics above, genius, it still required a remarkable level of ingenuity and insight to develop new mathematical ideas and see their interconnections. And in the words of the great French mathematician Laplace, read Euler, he is the master of us all. And what I want to encourage you all to do is that in each week from now up to Christmas, I want you to make a resolution to tell at least one person a week about Euler. Because Euler truly is the Shakespeare of mathematics. And I'll finish with, I think, an amusing observation that Tony Crilly makes about E in his book, 50 Mathematical Ideas You Really Need to Know. He tells us about the book on the right, a novel, Gadsby, of 50,000 words, written without using the letter E. One wonders why, sort of. Another winter in Cambridge. As Tony notes, I think this is nice, it is hard to imagine a mathematician setting out to write an E-less book, textbook, or being able to do so. So, happy Christmas. Look forward to seeing you in January for Fourier's series. And I'm going to continue in that lecture the beverage-related theme and discuss the best depth for you to have your wine cellar so that you will get a constant temperature all year round in the winter and in the summer. So do come along. Thank you.